In this problem, we're trying to find the magnitude of the force in this cable from A to B that's going to cause a moment about axis CD that has a magnitude of 500 pound-feet. So we need to find the magnitude of F that's going to make this true. And we're given that the moment around the CD axis, or the magnitude of it, is 500 pound-feet. So again, notice in the given, I have M sub CD with the bar over it. That means it's a moment about an axis, but the M does not have a line over it because we are looking for the magnitude, or we're given its magnitude. So we are not in equilibrium, but a diagram is still going to help us here so that we can have all of the relevant coordinates down. I will reuse the given coordinate system. All right, so C is actually located at the origin of it, and that's going to be important because CD is going to be used, that axis. I'm going to have a point A. This cable that I'm looking for the force in goes from A to B. So that axis is going to definitely matter here. And this is going to be my force F. And I have a point D, which again, this is the axis I'm going to want to know the moment around, is the CD axis. So C I know is at the origin, but I need the other coordinates down here. A is located at 6, 0, 0, and this is all in feet. D is going to be on the ZY plane, or the YZ plane, so nothing in the X. I have to go 8 in the positive Y and 6 in the positive Z. So 0, 8, 6 feet for D. And B is also in the YZ plane, so nowhere in the X direction. I have to go 4 feet in the Y and 12 feet in the Z to get to B. All right, and we'll see again why all of these are going to be important here. So let's see what equations we're going to need. Let's actually work backwards a little bit to know what are we even going to need to know in order to solve this problem. Well, we are looking for the moment around the CD axis. We know that that is going to be about the moment around any point on that axis, let's just say MC for now, dotted with the direction, which we can call U hat CD. So that's how we can compute the moment around the axis. We can also take the moment around D and dot it with U hat CD, but I'm going to recommend taking the moment around C here because C is the origin. It's always just easier mathematically to take the moment about the origin than another point, but it's not a big deal. MD would also work, and then still dotting that with U hat CD, that will still give us the moment around this axis, the CD axis. All right, how are we going to find the moment around point C? Well, there's only one force here that we have to worry about, so we have to do an R cross F. The force is just F, and then what's the R that we're going to use? Well, we want the moment around C, so it's going to start at C, and it's going to go to any point that F passes through. Well, we know it passes through, well, actually A or B, so we could use either one. I'll just use A here for simplicity. But if we used RCB, that would also be okay. And so let me just mark this is going to be RCA that we're going to use. All right, so in order to do this cross product, we are going to need to know the components of RCA. We're going to need the components of F. In order to use the dot product, we're going to need to know M sub C, which actually we can find that first and then feed it into that first equation. But we're also going to need to know U hat CD. In order to know the components of F, we also need to realize, since we're not given what F is, it's going to be its magnitude times its direction. And its direction is going to be pointing from A to B, so we can use U hat AB for that, and use that information to feed into the second equation. All right, so we kind of knew where we needed to end up, and now we have the building blocks to get where we need to go. So we're going to need U hat AB. We're going to need to know U hat CD. Let's start with those, because we can do those and then start to put some things together. So this will be RAB over the magnitude of RAB. RAB is going to be found by taking the endpoint B minus the start point A. So 0 minus 6 is negative 6i. 4 minus 0 is 4j. And 12 minus 0 is 12k. And the magnitude is going to be the square root of 6 squared plus 4 squared plus 12 squared. And that works really conveniently to give us an integer of 14. So I can now put this in decimal form, and if I can put it in decimal form, I do prefer that. Negative 3/7 I plus 2/7 j plus 6/7 k. Or we could have the decimal equivalent if we kept, let's say, 3 significant digits with it. All right, let's do U hat CD, which will be RCD over the magnitude of RCD. Okay, so taking point D minus point C. C is the origin here, so that's easy. 0 minus 0i, I won't even write that. 8 minus 0 is the j, and 6 minus 0 is the k. So 8j plus 6k is my RCD. And I guess I'll just illustrate that. That is this vector here, RCD. And now we need to divide by the magnitude. It'll be the square root of 64 plus 36 is 100. Square root of 100 is 10. So in reduced fractional form here, I will have 4/5 j plus 3/5 k. So again, this did work out nicely, conveniently, that I have these fractions that I can express my unit vectors in, so I'll stick with fractions. So I can start to work my way up. I can find now f expressed in Cartesian form. Again, that's f times u hat ab. Well, f I don't know. In fact, that's ultimately what I need to find. But u hat ab I now know. So this f can be distributed into my vector. So this is going to be, for the ab, negative 3/7 f I hat plus 2/7 f j hat plus 6/7 f k hat. Again, I don't know what f is yet, but f is the magnitude, therefore it's a scalar, so I can distribute it into this multiplication. And now I know f bar, I know f as a vector in component form. It's just that I don't know that scalar value of f, but I'll be able to find it along the way. So now I can work my way up. I can now find the moment around point C is going to be RCA cross F. F bar is the only force vector here, so this is going to be the total moment around point C. All right, so I need RCA, which is going to be A minus C is 600 feet. And cross F. So notice here, I am keeping that unknown magnitude F in each component because it's part of this vector. It's part of the coefficient in front of I, j, and k. And this will be all in base units, so this will end up being in pounds. My F that I'll eventually find is in pounds because everything's in base units. So this does look a little bit different than ones we've seen before when we take the cross product, but we can put a variable in there. It's not a big deal. And now when we expand this into its cofactors, I'm going to have 0, 0, 2/7 f, 6/7 f. The j is always going to be subtracted, will be 6, 0, negative 3/7 f, and 6/7 f. And then the k cofactor, 6, 0, that's negative 3/7 f, and 2/7 f. And expanding these 2 by 2 cofactors, I will have 0 times 6/7 f is 0, minus another 0 is going to give me 0 I hat. Then I'm going to subtract this j term. So what do I have here? 6 times 6/7 f is 36/7 f minus, well, it's going to be 0. So I will have a positive 36/7, and I don't want to forget the f there. And then my k term is going to be 6 times 2/7 is 12/7 times f minus, again, that will be 0. Right, so putting this together, I can just drop the I for right now. Actually, I will include it since I'm going to dot this. So net minus 36/7 f j hat plus 12/7 f k hat. And again, this is in component form, my moment around point C. I don't know what f is yet, but it's going to be in pounds. Going back up to my plan here, why did I care about this? Now I can go to that last equation. I want the magnitude of the moment around axis CD. So I need to take the moment around C that I just found and now dot it with U hat CD. So moment around axis CD is going to be MC dot U hat CD. So I'm going to have 0I minus 36/7 f j plus 12/7 f k. And I want to dot that with U hat CD. Again, I already found this. Was up here. So I can take that I already did, 4/5 j plus 3/5 k. And I'll explicitly put 0I here, but I'll have 4/5 j plus 3/5 k. And now I can execute this dot product. Remember, for a dot product, I am going to have the two vectors go in, but a scalar quantity come out. Because what I'm going to have here, I'm going to multiply the like terms, or the coefficients in front of the like terms. So I'll have 0 times 0 plus negative 36/7 f times 4/5, those are the j terms, plus 12/7 f times 3/5, the k terms. Again, notice on this line, there's no I, there's no j, there's no k. I get a scalar as my answer. So if I add this all together and I'll keep it in my fractional form, I get negative 108 f over 35. All right, so this is the moment around the CD axis. I'm really concerned about just the magnitude of this moment, so I will in the last step drop that negative sign. That's why it's going to go away. So I really care about the 108 f over 35. But here's the last piece of this. Remember, all the way at the beginning, I was told that the moment around that CD axis should be 500 pound-feet. If we're interested in opening this door or holding it steady, that needs to be the moment around the axis, 500 pound-feet. And F, the tension in that cable, is what we actually care about. So the last step here is I know that 108 f over 35, again, I'm dropping the negative because I'm just looking at magnitudes in this example. So 108 over 35 is going to equal 500, and this is in base units, pound-feet. Right, so the only thing I don't know at this time is F, which is the tension in that cable. So that comes out to 162. Everything was in base units here, so that F is going to be 162 pounds. So that is the value that's going to produce that desired result, having a moment about axis CD of 500 pound-feet. So again, the equation step, this one, we worked a little bit backwards because we needed to know what are all the things we're going to need to calculate to get our result. Well, it's the moment about an axis, which requires a moment about any point on the axis dotted with the direction of the axis. To find the moment about a point, we're going to need to take a position vector crossed with a force vector, and any vector, in this case the force vector, can be expressed as its magnitude times its direction. So I like to start by finding all the unit vectors we're going to need first, which was u hat AB, u hat CD, and then just running through the steps. In this case, not knowing the magnitude of f until the very end, but I can still find the moment about a point just with a variable. I can still find the moment about an axis just with a variable in it, and then equate the things I know at the end and get my final result.